Okay, so we have half a semester left. We are going to have so much fun. Oh, it's fun for me. Well, I mean, we'll get through magnetics and then we'll get to optics. Remember optics, you need to remember your geometry. Sophomore. Well, we get a crash course in it. We will have some fun labs where the lab will be like completely dark and you'll be reflecting light and measuring angles. And sadly, we didn't have the money to get the laser diodes this year. Wish we had laser diodes. But let's see. Who's taking a look at the assignment that's up? Let's do this Friday. Okay. Did you look at question 2? Kind of. So, like, I have a question. What is the, first off, what's this? Dot product, what does it equal? Nope. Nope. No, we need the other one, don't we? You remember when we did this in like the first week? Yeah, there you go. Yeah, we don't really need the parentheses. That's going to be helpful. For question 1, it'll be helpful. And then on question 2, I'm not going to actually make you show me the parity operator. Just remember that, so if we, where's a good space here? Not a ton of space. Okay, so if we're thinking about, you need to figure out, you need to remember how to do a matrix determinant. I've done it in here multiple times. The parity operator is either a +1 or a -1. So the way the parity operator works is you're going to look at the row and column you're in. If they add together to give you a positive number, it's a +1. If they add together to give you an odd number, it's a -1. So if I look at row 1, column 1, so that's going to be your I hat, because you're reducing a 3x3 into 3 2x2s. So you see how row 1, column 1, that's 1 + 1 = 2. That's a +1. And so then remember, everything that's in the same row and column as that I hat is not being considered. Now, when I go to the J hat term, That's row one, column two. 1 plus 2 is 3. That's going to be a minus j hat. So the parity operator gives you a -1. And what did I leave out of that 2 by 2? Yeah, so I see the row that j hat's in and the column it's in. That row, that column are being left out. So then your third one, your k hat, that's row one, column 3. 1 plus 3 is 4. So now you're going to get a positive k hat. And then that's going to leave ax, ay. And so you go from a 3 by 3 determinant to 3 2 by 2 determinants. And then you need to look at how to solve, you need to figure out how to solve a 2 by 2 determinant, which will end up leading you to the equation that'll give you each individual component of your new vector. There's a reason we do this. What is the physical significance of turning your of a matrix? What is the physical significance of that 3 by 3 matrix? What is it doing? You don't get an answer. She already knows the answer because we've been using matrices and group theory, and so you're very, very close actually. A matrix is going to be a map of your system. It's not just this block of numbers. It's a map. So here you see you have your ijk's directions. Those are going to set up a coordinate system. And then these vectors that you're crossing into each other are actually going to line up as a parallelogram within that space. So what happens, instead of having to use like your right-hand rule and say, well, which way is the vector of this cross product going to point? You solve for the new vector, and if you were to map that vector on the same ijk space, you would notice that it's going to be perpendicular or orthogonal to each one of the original vectors, which is what we've been doing with the right-hand rule so far. Because it's a parity operator. You see how j is in row one, column 2? 1 plus 2 is 3. That's an odd number. So a parity operator, an odd number, gives you a negative sign. Keep in mind, I still left out the top levels of this representation. And this is the more exact explanation of the physical space that you're working in. That's why when you get the quantum mechanics and you're looking at like particles, you end up in what's called Hilbert spaces, which are in spacing. So particles can live in hundreds of dimensions simultaneously. Had a lot of fun over break, and I feel super happy because the handcuffs have been taken off. When I first got here, the dean we had at that time, my own department, said, well, you can't make them do this level of stuff. So fine, so I held back for a number of years. We now have administration that says, no, we're not going to do stuff down. We're just not going to do it. You're going to leave here better than your contemporaries. Well, I mean, it's really up to you. Some of you will not like it, but you'll learn it. Some of you will hate it and refuse to learn it. And some of you will enjoy it. It's just kind of the way it goes. But you're going to leave here knowing things that your contemporaries will not know. Because I made mention of the fact that there's only so much I'm allowed to teach at certain levels. And I was asked, who told you that? And so I told this person the story, and they said, yeah, I'm not anymore. So we're going to do things the real way. Uh-huh. Good. Yeah. Yeah, so like if you took out your A, that's still, so that's row two, column one, so that first one would be negative. You know, row two, column one gives you a three. So that would be negative when you parity operate. And so then, of course, your two by two would be your JK and your BYBZ. The two by twos are pretty straightforward. You just need to look at how to solve a two by two determinant. Hey, the good news is, technically, this is still algebra. It's linear algebra, but it's still algebra.
I love
You mean not foiled?
I just don't like, I can't.
Oh, okay.
I just hate, like, I struggled with it so much in my school. When I figured it out, and I just hate it. I just think that's more than that.
Well, so
My bad.
the thing is we're not gonna do things at the topmost level, but we are going to add stuff. It's like, this is the real way we do it. Since I'm not limited anymore, we're not gonna make asinine assumptions and say, well, we'll just call it this. No, we're gonna do real stuff. Again, I know most people really don't like math. I know most people avoid math because they just don't want to do it. I don't know, after several years of trying to gently coax people to do math and getting it rejected over and over and over again, I've kind of been broken, so now I don't care. I don't care if you don't like it. It's a language that teaches a logic that a lot of people don't have. And oftentimes when I'm grading homeworks, I can see that logic missing. Because there are days where I think some people wouldn't know a non sequitur if it kicked you in the side of the head. Non sequitur? What? Can you translate that? It's a term that you learn in logic class. It means does not necessarily follow. So I'll see jumps on the assignments. People will write like a certain step and then they'll jump to the final equation. It's like, you don't actually know how to derive that, do you? Because you can't go from here to here. Because, well, then that tells me you looked it up and you didn't go from here to here. Then if you solve it below, circle it, draw an arrow back. Yeah, but well, that's always the funny thing when I get something that's very clearly someone looked up on AI. It's like, why did you think I wouldn't notice that? Like, you really don't think I know how to do these steps in every single one of these derivations? You thought I wouldn't notice that jump in logic? That I've seen. Yeah. As long like you draw your arrow back going, actually, this should have went here. That's fine. I mean, I also don't mind because I also know that I have students who have excellent logic. They just write in a spiral. Most people do, but most people don't derive, twist, derive, twist, derive, twist. Like, no, I really don't understand biology. But yeah, that's why, again, that's why like last year when I was having a bad day, I said, I reject human, wish to return to monkey. And someone went, it doesn't work that way. Let me have this one. Okay. So these notations here, your dots and your X's, make sure you understand what these are. You're going to be seeing them quite a bit. Because if we want to be able to keep the movement of a particle in 2 dimensions, you want to keep your particle moving in X, Y, so you can solve it, we need to represent magnetic fields as going in and out of the page. Magnetic fields into a page is a dot. Magnetic fields out of a page. So these are vectors. So a vector into the page is a dot. A vector out of the page is a cross. Okay? Because you're going to see this representation. And it's actually quite an astute meme. Does anyone get it? It's another one of the oddities of magnetism. So a moving particle in a magnetic field experiences a what? Force. A stationary particle in a magnetic field experiences a what? Nothing. So technically, yes. And it's weird. You would think it's the same charge. Why doesn't it also experience a force? Welcome to magnetic fields. So if you get yourself supercharged and you start walking in a certain direction, you would feel the Earth's magnetic field pushing on you. However, if you stood still, nada. I mean, you'd have to get super. Yeah, the kind of charge that if you grounded, you would die. But it's just you don't. We're not even going to try. No, you can't be grounded, and it's not necessarily touching. It's a certain it's a discharge distance. That's why you ever seen the people who work on power lines? The reason they don't die is because first off, they're high enough. You ever seen the videos, the guys up on the power lines, they can run their hands across and you'll see like Thor, like lightning coming off their hands. Well, but they're so high up, they can't ground. Yeah. That's why birds don't die. They're high up and then the distance between their little feet is so small that it cuts that current down so much, it doesn't kill them. Okay. Yeah. Yeah. Did you know that a physicist named Michio Kaku, when he was 17, made every single transformer on his street blow up? He built something called a Betatron in his parents' garage. They were super happy because they're like, that sounds really smart. Go ahead and do it. And he didn't account for the massive magnetic field of a particle accelerator. And he blew up the transformers. So it is. You build a machine in your garage, it causes the electricity in like that side of town to go out completely. Oh yeah. Now, we were talking about the Earth's magnetic field and what it does for us. Talking about how the northern lights are a plasma discharge at the apex of the magnetic field. Talked about why when people were going, the northern lights over the hospital, it's so pretty. It's like, you really have no idea what you're talking about. Great, take pictures. Take pictures of our incoming death. That's awesome. Well, it could signify a number of things. It could signify the beginning of a magnetic pole flip, which I mean wouldn't necessarily be it wouldn't necessarily be an extinction level event, but it would be pretty catastrophic. Because why? What causes the Earth's magnetic field? The core doing what? Moving. So it's spiraling around. You get a lot of charges moving, which we're going to study. You get a magnetic field. Well, what would cause that what's one thing that could cause that magnetic field to flip over? One of the things that could cause it is the core stopping completely and then going the other way. So that'd be a pretty intense geological event. Like that's probably the thing that would cause Yellowstone to erupt. So, you know, the magnetic poles flipping can have a number of pretty catastrophic causes. But, you know, for all of you who are trying to equate physics knowledge to medicine, if we did not have our magnetic field, this is just a few of the issues we run into. The radiation coming in would cause a nervous system discharge, which would essentially cause you to short circuit. You would get all kinds of cancer, degenerative diseases. Your eyes would fry. The rods and cones that make sense of light would be melted. You'd have almost instantaneous radiation burns, which burns are bad. The radiation burns, imagine like a 3rd-degree burn showing up from the inside out. Not to mention the gamma rays coming off the sun. You know, I've said before that essentially they liquefy DNA. Let's be more exact about, I use the word liquefy to try and explain the process. Let's be more exact about what they do. Let's think of DNA more as a crystal. But what happens if you shoot a marble at a crystal? It shatters them. That's what the gamma rays actually do. They shake the amino acids apart. So, I mean, if you think of turning a larger structure into a bunch of smaller free molecules of liquefying, you know, kind of like ice turning into water, sure. More exactly, the gamma rays would shatter the peptide bonds. They would also disrupt, for example, the intermolecular forces inside the DNA that's causing it to unravel. So, no, not cool. Listen, little Gru, not cool. We are going to steal the moon. In terms of money, we have no money. Well, that's a very truth-telling statement. So we're very, very grateful for the Earth's magnetic field. We're very grateful for the Earth's magnetic field, and we don't want it to change at all. Oh yeah, but it's very, so that's one of the issues. When you hear people talk about have you ever heard someone talk about terraforming Mars, like Elon Musk or something? Do you know why? Do you know why that's completely wrong and can't happen? Like terraforming Mars into like a new colony of Earth. So that's part of it. It also has to do with the size of Mars. Mars is actually only a little bit bigger than our moon. So 2 problems. Mars's gravity is not strong enough to hold a dense atmosphere. The magnetic field is also much, much weaker than ours. So this solar wind would strip off most of the atmosphere you put in there. It'd probably ignite the oxygen. So you could have dreams of terraforming Mars. It's just not going to work. Now, interesting little geological thing for you to ponder, think about. The moon of Titan, not Titan, the moon of Jupiter called Io is an ice moon. However, unlike most moons, it has no craters on its surface. Why? Well, it'd still have craters, right? There's an ocean underneath it. But what does no craters on the surface tell you about the ocean underneath it? I didn't say yes or no. No, there's an ocean underneath Io's ice. But what makes it so that there's no craters on the surface? Nope. It's being constantly replenished by the churning ocean underneath, which means that the ocean underneath is liquid and moving and very likely alive. Yeah, not fish you want to meet though. So here we go. Say you have a proton moving toward Earth and interacting with Earth's magnetic field. Okay, so first off, proton moving towards Earth. Which way is it moving? If you had to put this on axes, which way is it moving? Because I asked.
No, why?
Yeah. Which way? But negative y, which is which way? Down. So make sure you're able to take apart these questions. I love how you immediately went to. But so the part of the protons moving down. The velocity of the proton is 6.0 times 10 to the 7th meters per second. And the Earth's magnetic field, let's see, is going to be 6 microtesla. What is the magnitude of the magnetic force on the proton? The magnitude of the proton's acceleration and the direction of the magnetic force on the proton. All right. So let's see. Okay. Well, yeah, so let's think of it this way. This is going to look a little odd, but try to picture this. So we know that this direction is down. Which way is B going? What do we mean by up in this case? Which way do the magnetic field lines of the Earth run? Well, we'll get there. So there's a couple of ways we could write this. I did it this way to start with. So the particle's moving down. Which way do the magnetic field lines of the Earth go? Yeah, which way do they point?
Down, back. How do we?
So they point north. Why am I able to represent it this way? What angle do down and north make with each other? Right angle. So no, down is technically down. On a line going straight into the center of the Earth. Down. My psyche, the more guesses you make, down. Because if you're moving down, which way's north? I get turned around in here. So, yeah, up, yeah. So if you're going so if you have a particle, we can represent it this way to get the idea of that of that 90-degree angle. So if you have a magnetic field going that way and a particle going that way, they're at 90 degrees to one another. So we can represent it on a 90-degree angle. Yeah, well, if you keep asking me questions like that, I'm going to make you represent it like this. Well, that's going to be the force, but I'll make you do that. Well, technically that would be down, so that's, you can call that one the velocity. Ask it again. No, you just need to be able to represent these at a 90-degree angle to each other. Well, no, but you're thinking of these directions as north, south, east, and west. Uh-huh. Why are you circling it? Think of it like a differential. Your north vector right now is a straight line. If you look at the whole Earth, you get the lines that wrap around, but for like your immediate position, it's going to be a straight line. It's a tangent to that curve. Right. So what we need to figure out is the force on this particle, and we're going to start by and we'll finish this the next time we meet, but we're going to start with our notion of the magnetic force, which is yeah. And then you'll have to think about which way the magnetic force is going to make it go.
No, wait, actually, I don't know. Actually, would never make it.
Well, look at your V and your B. Take your right hand, cross, like however you do it. I do it by rotating my fingers. Cross your V into your B. Which way your thumb pointing? That I don't know. So put your fingers along V. Rotate it into B. Which way is your thumb point? So if you're looking at your iPad, which way will that point? So if you look here, you put your fingers in the direction of V, you rotate it into V.
Oh, you literally just like, you just know your fingers.
Yeah, that's the way I do it. I showed you, there's multiple ways you can do it. But you think you're the cross product, you're crossing the vector V into V. So since your force is going to be coming straight out of that screen, that's why you use the dot.
Okay.
I decided to just start printing my labs. You know, I'm online, but I'll just start bringing them to you.
Okay, that works.